See, this week we had to the test from last module, and we started 3.01 just because we got to get some things done. And you guys are doing well. Everyone's caught up. Everyone's taking the test. Everyone did well on the test. You guys are understanding, doing fabulous. So, great group of students here that we have in our pre-cal class, which I knew you would be at the start of the year. So I'm like, no problems at all. But today we're going to cover 3.02, 3.03, 3.04, and they're all related. They're all basically, 3.02 is about exponential growth and decay. And then the next two lessons are logarithms, which logarithms are good stuff. I'm excited to get into logarithms today. So let's talk a little bit about exponential growth and decay first. All right, so lesson 3.02 talks about exponential growth and exponential decay, and they give a couple of formulas right off the top here that they say y equals AE BX, where B is greater than 0. Right, and then they go into use entirely. There's different formulas people use for exponential growth or decay. This is one of the ones that's common, where A is basically your starting amount, and then it's e to the power of bx. X is usually your time period. B is usually your rate of growth. For exponential decay, it's very similar. It's AE negative bx, where B is greater than 0. The B itself is actually less than 0 because it's negative, but there's a negative in front of the B. And we have some graphs of what that looks like. Let me go ahead and show the graphs real quick while we're talking about that. So the graphs from our lesson on what the exponential growth and exponential decay look like are this right here. That's what we see is exponential growth. So those where it has an asymptote at y equals 0. And the same thing with the decay. It won't ever quite hit 0 with the model that we have, but it'll keep approaching it closer and closer and closer. So there is the graphs they give us for the exponential growth and decay. So going back to that, let's talk about a model. And they have another logistics growth model that we're not really using at all. So you can see that in the lesson. I'm not going to spend a lot of time on that. What you'll commonly see, and we're not really using this model as much as we talk about P0. That's really in any growth and decay model. This is the initial population, right? How much do you start with? If you're going to have growth or decay, you have to have an amount that you begin with before things start growing, before things start decaying. Okay. And then generally the model you're going to have for that, the formula you're going to have is you'll have that P, and they'll usually put it as a down here, P of 0, because we'll say P of T, and that'll be P of time, right? It'll be P sub 0, which is basically what did you start with? And you'll multiply it by 1 plus R to the t, where t is your time periods. If you're talking about something that exponentially decays by the day, then this will be how many days of decay we've seen or growth that we've seen. Or maybe you're looking at an interest in a bank account that grows exponentially, and this is how many months that they calculate it once a month, and t would be your months. But the important thing to see here, if you want to look at this in an actual model, if we had, let's say 100, and the number we were multiplying by 106 t, what we see is we start with 100 of whatever we're talking about, and this is a 6% growth, right? If this was just being multiplied by 1, there'd be no change, right? It doesn't matter how many months we calculate. If it's just 1, it'll never change. 1 to the 10th power is still 1, so it doesn't change. But 1.06 means we have a 6% growth. So a lot of times you'll see problems where it'll ask you what is the growth or decay of that. If you see a 0.97 to the t, then this is a decay. Since it's less than 1, that means the amount is shrinking, right? So less than 1 is decay, greater than 1 growth. So it either grows or decays based on what number is in that parentheses generally. So they have a 1 plus r. So r is the rate. R is the rate of growth or the rate of decay. So when you get into the problems for this lesson, the practice problems after that, it'll have determine whether this is growth or decay, and find the percentage, the constant percentage rate. Well, if we look at that, we say, well, that is growth. It's obviously growth because it's 1.06, and it is 6%. Right? It's a 6% growth because it's 1.06. So that would be like some of the problems I have. In fact, when I'm looking at our problems on here, we have two problems. The first two problems are both identifying what is the rate and is it growth or decay. So then the next two problems we have in that are talking about actually finding the function that satisfies conditions. So it'll tell you the initial value. Okay, so initially we had 50, and then it's going to increase at a rate of 17% per year. And I want you to find what is the proper function for that, and it'll give you choices. And of course, on this case, we'd be looking for f of t of 50 times and 17% increase 1.17 t. All right, times 1.17, because we're seeing a 17% increase. If this was a decrease, then we'd be looking for 50.83 t, right? Because it'd be 1 minus 0.17. Start with 1. Since it's a decrease, it goes down 0.17%. So it summarizes to 0.83. That's the type of things we're looking at on there. And then our last problem on that is just gives you a function and wants you to say, okay, after 26 years, how much do you have? So like if this was after 26 years, you'd put a 26 in there and calculate to see how much you would have after 26 years to the nearest milligram or whatever it tells you to do that to. So exponential growth and decay, it's just a matter of recognizing which it is, growth or decay, and being able to use the formula. So I don't think it's anything that we need to spend a lot of time on, but if you have questions, we can certainly review that either today or next week in class. We don't have any more class this week. Just a reminder, this is teacher meetings the next couple of days, so there's no class meets of any kind in any of your virtual classes. So just today, and then you're off for the rest of the week. So get a nice little break there. If you're all caught up on everything, makes things simple. All right, let's look at lesson 3, because then we get into logarithms. And logarithms are a very useful thing. When we talk about logarithms, When we start out in mathematics, we learn about addition and subtraction and how those are opposites, right? If you add something and you want to undo that, we subtract it. If we multiply something and we want to undo that, we go back and we divide by the same number, and they just cancel each other out. Well, logarithms are actually the opposite of exponential, right? So if we have exponential, the logarithm is what cancels that out. If we have y equals 2 to the x, then log base 2 of x equals y. These will cancel each other out. I'm sorry, that's for the inverse of that one, but yeah, we'll get to that. We're going to do some examples. But logarithm is the opposite of exponential. It's how we undo an exponential. So let's get a little bit into that. So the definition of a logarithm, all right, we've got some parameters let's start with the x. X is greater than 0, and 0 is less than a, but a cannot equal 1. Then y of log base a, y equals log a of x, log base a of x. And I'm gonna use this term. You'll see this in college. Some professors use it. This if, an if with two f's. This means if and only if. If and only if. So I'm abbreviating that to it. It's an IFF with two f's. If and only if x equals a to the power of y. So these are the opposites there. If x equals a to the power of y, then y equals the log base a of x. Okay, those are the opposite things, and we're going to play with that and look at that. So let's do an example. So if we have log base 3 of 27, what does that equal? Well, if we look at this, 3 is the a right here. X is what it equals. I'm sorry, x is 27. So 27, right? Substitute that in there. That's our x. That's our x. Equals the a is the base. 3 to what power? 27 equals 3 to what power? So log base 3 of 27 is 3, because 3 to the third power, 3 times 3 times 3 equals 27. So log base 3 of 27 is 3. So basically, when you see a log, it's like this to what power is going to equal that. This to what power equals that. So that's kind of how that works as far as counterbalancing the exponential, where these numbers fit in. On our calculators, even the simplest calculators, they have log, right? It just has a log button. It doesn't have a base number. It's assumed log 10. If you do not see a number down here, it's assumed log 10. So if you go to any calculator that has a log, and like I say, even the cheap $5 calculators usually have log, and you put log 100, it'll equal 2. Because 10 to the second power equals 100. Log there. If you put log 10 or log 1, what answers will you get? Well, 10 to what power equals 10? 10 to what power equals 1? Log of 1 is 0, right? Because 10 to the 0 power will equal 1 in that case. So that's just a basic look at logs. So this is the common log. Base 10 is the common log. That's where you don't have to write anything. If you just write log without a base, it is assumed to be 10, because that is what's known as the common log. So let's talk about some of the properties of the logarithmic function. Properties. Some things to know was always true here. So log of any base, a, of 1 equals 0. Doesn't matter what base. If you're taking log of 1, it's going to be 0 because it doesn't matter. Any number raised to the 0 power is 1. Right? Any number. How about log A of A? What power do I have to raise this to equal itself? That's always a 1. If these two numbers are the same, it's always going to be a 1 because it's going to be this, the first power equals itself. How about this one? We have log A of A to the X power. Log of A to the X power. Let's look at an example of that. So if we're trying to understand, sometimes it helps to have an example. Let's look at log 3 of 3 to the second power, which is 9, right? 3 to the second power is 9. What do I have to raise this to be 3 to the second power? We'll have to raise it to the second power. This is always going to equal X. Because A to the X equals A to the X. This one because A to the first always equals A. This one because A to the 0 power always equals 1. So because these are true, this is the properties of these logs. All logs are going to work with this, regardless of what the A is. And here's one more. Log A of X equals log A of Y. If that's true, then X equals Y. So if log A of X equals log A of Y, and they have the same base, so both log A, then X must equal Y. If these are equal, those have to be equal. That's kind of common sense, but it's one of the properties that we need to be aware of. Know that works every time. So let's look at a couple of examples of how this might be used. Some of these properties here. So in the examples they give us in our lesson, if we say log 3 of, and they put this in parentheses, because otherwise it's just log 3x. If we don't put that in parentheses, we're just talking about x and then adding 4 at the end. But put in parentheses, if that equals log 3 of 10, then using this property, that means x plus 4 equals 10. Log 3 of this equals log 3 of this. That means these must be equal to each other. So x equals 6. Right? We can use that to solve that equation. If we have log 7 of 7 equals 2x plus 1. We don't have a log over here this time. But we do have log A of A, so it has to equal 1, which means this must equal 1. Right? So 2x plus 1 must equal 1 because we know what a log of itself equals. Subtract 1, 2x equals 0, so x must equal 0 in that case. So we can use these properties right here to solve equations involving those type of things. So when we graph, we can transform graphs of log functions, graphs of logarithmic functions. So since it's the inverse of an exponential function, when we sketch it, it's basically reflecting the exponential function across the line y equals x, right? Since they are the inverse, it's an inverse of the exponential, just like, it'll undo exponential. It's the inverse. So it looks very much like the exponential that we saw up here, except it's reflected over that diagonal y equals x line. So when we see y equals log of x, log 3 of x, that's the green one right here. And we can do transformations with this. If we do, this works very much like any other transformations of graphs. If we take the x and we subtract 2 from it, it's in parentheses, so it's bound with the x there. That moves it 2 to the right, just like other transformations. When we have a quadratic equation, for example, and we have that -2 in the parentheses, what it does is it moves it 2 to the right. So we see the same thing with logarithms. If we put a -1 at the end, just like any other graph, linear, exponential, whatever, what that does is moves it down 1 on the y-axis. You see on the graph on the right, it moves it down 1 unit just by putting this afterwards. So transformations with these graphs work very much the same as they do with the other functions that we've looked at previously. So that will be very similar. We're also going to introduce, we've got all kinds of fun things that we introduce in math, right? We had pi, we had I, which is imaginary number. Now we're going to introduce, if you haven't seen it before, E. E is a number in mathematics. We ran out of numbers and had to start pulling in letters to be numbers. E is, and I'm going to say about, because I'm rounding it at some point, 2.718281828. All right, so it's a repeating type thing here. E is a number, and we use that in logarithms as a base E. You'll have some log base E, and it's not just a variable E, it's talking about this number. Log base 2.718281828, continuing on. But we actually use that so commonly in math that it has its own symbol. And you'll have calculators have that. If you say ln, this is called the natural log. The natural log. Let me write that down. Natural log. And so we use this instead of writing log E, we use this. So if we just say log E of X will be the same thing as ln X, and that's assumed to be a base E, all right, where X is greater than 0. So when you see this, that is a different button on your calculator, and E is actually a number. So the same properties apply. Ln, well, make it look like a 1. ln1 is 0. ln E is 1, right? Because this is assumed to be a base E. We just don't write the E's when you put ln. ln e to the x equals x. If ln x equals ln y, then x equals y. Right? These are the same properties that we saw on the logarithm functions, because these are just logs, just like the others are. It's just using base E. So ln is just using the base E. So you will see that on most calculators. You'll see this ln on the calculators for the natural logarithm. All right. So, if you do, by the way, on the calculator, if you do this ln of -1, I put that in parentheses, that'll give you an error because we had this little caveat here. X has to be greater than 0. Has to be greater than 0 for logs. So let's test some things. Let's try this. Let's see. Oh, no, I know what I want to do. I want to look at the properties, the additional properties we have in lesson 4, because this is just introducing E on there. Here's some useful things that we learn in lesson 4 is change of base. Change of base, very useful, because what if you're trying to solve some logarithm problems and you don't have your nice calculator? All you have is one of those $5 calculators. And all it has is log or natural log. And you are trying to find log base 4 of 27. And we know right off that 4 raised to some power is not going to be a nice number, right? It's going to be some complicated number. 4 to some power is 27. We don't know that for sure. So we have a change of base formula. If all we have is just a cheap calculator, just has log, then we can solve this by using this formula. we take the log of 27 and divide it by the log of 4, that will give us the same answer as the log of 427. And just doing this in the calculator means these are both base 10 because I didn't give them a base, right? Those are both base 10. So let me see. I was having to charge my calculator this morning. I didn't have it all charged up. Critically low. Okay, I don't have very much. I don't know if I'll be able to do this fast enough. But let's see. Where is my log button? Sorry, there's my log buttons right over here. Ooh. All right, calculate. Mine is in blue right above down here. So if I do log of 27 and I divide that by log, and it's letting me put base because this calculator will do that. So that says that is 2.3774. Let me go ahead and do, see, it made it base 10 automatically, if you can see that. If I did log, and I can put the 4 and put the 27, I can actually type it the way it wants it. Same answer, 2.3774. So this change of base formula allows us to solve more complicated other bases other than 10 or the natural log, just being able to use that formula. So that is a very, very useful thing to get us out of a jam when we don't have the proper equipment or can't figure out, maybe we can't figure out how to do this on whichever calculator we're using. We can always convert and use that. So change a base for logs. Natural logs work the same way. If we did this in natural log, we could do this ln of 27 over ln of 4, and it would work the same way. We would still get 2.3774. Doesn't matter. Whether we use log 10 or log E, it doesn't matter. Change of base works however you want to do that. So let's add some more properties to what we had up here, other than this change of base, which is a wonderful thing. All right, let's say we have log A of U times V. All right, so we got two numbers in here being multiplied together. That is the same thing as log A of U plus log A of V. Okay, log A of U, it's plus. When these are being multiplied, we take the log individually and we add them together. If we have log A of U divided by V, then we have log A of U minus log A of V. All right, so when we divide, we're subtracting. Let's see. Oh, here's one that's used. If you have log A of U raised to the n power, U raised to the n power, this is the same thing as n times the log A of U. So you can bring that, when you have that situation, you can bring that out front and just multiply that by whatever the log of U is, base A. All right, and these work the same if they were natural log. You know, UV would be ln U minus ln V. So I'm not going to write all those again, but same thing. If it was divided, it'd be ln U minus ln V, or n times ln U. All right, so what this allows us to do is expand logarithms. So let's do one of the examples they have here, just to talk about what it's talking about. So if we have ln x to the third y squared, and we need to expand this, and they say expand this logarithm, we say, okay, well, the first property that we looked at says if we multiply those, that's the same as ln x to the third plus ln y squared. Okay, so that's the first step, because multiply means we can add those. And then the last property we looked at said if this is x to the third, so this would be 3 times ln of x plus 2 times ln of y. And that is fully expanded. So if it says to expand the logarithm, this is what we're looking to do. We start with all 1 and we're breaking it down to single logarithms as far as we can break it down. If we had, let's do another one. If we had log base 5 of xy divided by p, we got a few things going on there. Right, since this is a divided, this would be the same as log 5 of xy minus log 5 of p. And then since these are multiplied, it'd be log 5 of x plus log 5 of y minus log 5 of p. Fully expanded. Fully expanded. Started out with 1 log. We expand it as far as we need to. Of course, if we can do that, that means we can also go the other direction. So if they give us log x plus log y minus 2 log p plus log q. Okay, well, the first property, so anytime we add it, it's the same as log x times y minus, oh, this is being added too, so we can put the q with that. Those are all being added. So those are all being multiplied together. Minus the 2 log p, because it's being subtracted. So that was from the first property. Then we look at this right here. We make that log x, y, q, because minus log p squared, because we had that property. And then finally, this is subtracted. So we have log x, y, q over p squared. Go in the other direction. Anything that's added, we got to multiply those together. Anything subtracted, go to the bottom, and we use that property to write that back as a p squared. So those are our logarithm properties. And so with our lesson this week, we'll be evaluating some logarithms, be expanding some logarithms, all of that kind of good stuff. But this is not that complicated when you realize it's just taking the exponential and it's the inverse operation of exponential. So pay attention to that. Don't get lost in it. Remember what you're doing when you have that log to a base with a number. What number do you have to exponentially make that base by to get this number? Log 2 of 8. I mean, 2 to what power be 8? 2 to the third power is 8, right? So log 2 of 8 is 3. So as long as you remember how logarithms work, I think it'll be fine. Take your time. Don't get careless with all these properties. But I would have all these properties in your notes. You know, when you get to take quizzes and tests and all the good stuff, you can always use your notes. So it's good to have all of these properties written down in one place with examples so you understand how they work. So if you have questions, hang around. Otherwise, have a good break. We'll see you next Tuesday. So we don't have anything else, no other meetings this week. But there you go. Have a great week.
Let's get out of here. Word to your multiples. Math, baby. We're learning math, baby.